Hi, this is insyaAllah, the last part of chapter number 15, Oscillatory. So part number 3. Let's have a look at the textbook. Alright, this portion, I am going over example 15.4 once again, but only to describe why we choose the negative portion. Okay. Look at example 15.4b. Now, notice that, sorry, not B. A, alright, A. Now, I believe you might get confused. Why do we choose the negative if we just solely depend on the word provided or the statement provided by the book? So I'm going to help you out with drawing the idea. Okay, just recall the case itself. So it shows that this object rotates counterclockwise and it's moving to the right So at time t, distance travel is not distance. It started at 2 meter, and since it's moving to the right, meaning that it's trying to go to the maximum amplitude. And in this case, maximum amplitude is 3. So in short, if we create a graph, it probably looks something like this. Trying to go to the amplitude. Okay, so this is where the time is 0. This is t. And this is where the amplitude is. And if we try to complete the graph, then it would look something almost like this. Okay. Now, so therefore, since we would like to use the expression meant for cos, okay, for cos, then we have to do a little bit of magic. So before we do the magic, right, cos graph started here, the red colored, the red colored. And therefore, we need to do a little bit modification and of the phase itself, the value of the phase. What is phase? The whole product in the bracket. Okay, so we have to throw away this portion. So throw away this portion, resulting the negative. Understand? Right. Let me show you. I certainly hope I have a few pictures. Okay, I have this picture. I'm sorry. So this is what the opposite of what I want. All right. Okay. Now, let's look at this. Okay. Okay. And this is trying to indicate, okay, you will find that when you open different textbook, certain textbook choose that displacement of graph sinusoidal is using sine. No problem at all. It's just that for standardization, the book that we are using is using cos. So yeah, so we stick to that. All right, never mind now. A graph that is sine, okay, is a sine graph supposed to look like the red one. This red one started from 0 to small cap, right? Very similar to our graph, which is velocity. Okay, velocity graph. Now, in the case of the black one, which is x number 2, this is x number 2, right? If we still, let's say, it's actually cos because it started here. So see that it's omega t, complete omega t without no phase. But let's say that you want it to be sine. But bear in mind, I'm just discussing about the technique, how we use plus or minus, right? Now, so if I still, if let's say that I want to use similar as what this technique shown you, which is sine, then you will find that I am missing another piece here. Then only the green complete with the black becomes sine. And because it's missing, then I add them up. Understand? Alright. If let's say I'm using for x number 2, x1, I would like to convert it into cos. So it will turns out to be a cos omega t. Okay. I need to throw this away. So throwing means minus pi over 2. So that is the phase constant that I need to minus so that my equation would be modified and customized solely for cos. Right. Alhamdulillah. Let's have a look at the next subtopic. All right, this is our almost last. No, we have another resonant. Okay, two more. Pendulum and resonant. All right, pendulum is another example or model that behave in simple harmonic motion. So just now we have spring, and another is now pendulum. Now, what does a pendulum do? If it's supposed to to oscillate in simple harmonic motion, then the motion would be back and forth, right? Okay, now, so being back and forth, then we will find there was this force, okay, in the direction parallel to the motion shown by this book. Okay, look at figure 15.15, mg sine theta. This is the force that enable this bob or this mass to swing back and forth, to the right or to the left, to the right, to the left. Okay, and therefore this is the restoring force. This is the restoring force. Since this is the restoring force, previously Hooke's law, Kx is the restoring force. Now that's the reason why there is an indicator that is negative here, negative mg sine theta. So like replacing Kx, but negative Kx meant for spring. So this one meant for pendulum. So negative mg sine theta. And from here onward, they do mathematics that Kx is equivalent to MA previously. So in this sense, it becomes negative mg sine theta is equivalent to MA, and then this simplified twice. There was this derivative towards displacement, which displacement uh, is actually equivalent to SL theta. Okay, I'm not going over too much detail here, but the idea is supposedly something like that. Okay, because my concern is this one, two things. Okay, two things. Number one, from this calculation, when you simplify, you will end with a product of G over L. Sine theta becomes theta. Sine theta becomes theta. This is what you will find. Now, why is it as if something happened to the sign? No. What really happened is when pendulum exhibits simple harmonic motion, there is one condition, syarat condition. The condition is the theta must be small enough, in fact, smaller than 10 degree. Okay, certain textbook says 12, but this book says 10. No problem. Okay, now why? Because there was this approximation that will occur. When it's small enough, then the product of sine theta will become equivalent to the theta. Okay, example. Now, sine 10 degree, convert it into radian, okay, then it will become 0.20, 0.028. But take your calculator, 10 over 360, sine them. You have the same answer. Okay, so 10 over 360 is 0.28 as well. So this is what it try to portray, and you can try with another example. Okay, another example. But basically, textbook, I remember another textbook which is survey as well says that it's 12, but I disagree, more or less towards 10 lah. Right. Now, this is the core that you must understand. Okay, the portion where the derivation and such to is to come to the conclusion of this angle and also this one. All right, and in the exam, this no, it will not be tested in the exam. Right, it was more on the understanding how we arrive with that idea. So we arrive with this equation, which I tend to call as talak. Okay, just recall something. So previously we have 2 pi square root m over k. This is when you deal with simple harmonic motion involving spring. This is what I call as talak. Okay, what is L? This is a length of the pendulum, while this is 9.8, positive 9.8 meter per second. When should we use negative? Well, when it's free fall, when it's kinematic in a free fall, then only you use negative. Other than that, no, none. Right? So this will allow you to calculate the amount of period, means what period? If the pendulum starts swinging from here, then the time taken to return back to its original position. So in my case, start from right, return to the right as well. So that is the amount of time that you can calculate based on talak or this equation. Right. Okay, now not so interested. Okay, let's look at this example. Very simple. Huygens, the greatest clockmaker in history, suggested that international unit of length could be defined as the length of a simple pendulum having a period of exactly 1 second. Now, how much shorter would our length be if his suggestion had been followed? So he says that, like, please follow my suggestion. This pendulum will give you 1 second. So whatever length that is, that should be our SI units. Okay, our SI unit. But no, no. All right. So from the expression of talak just now, so the book tend to rearrange. No need. You can just start from the very raw L over G. So you will find that this is 9.8. T is 1 second. So arriving with L 0.248 meter. So meaning that our SI unit should be like this length. Okay? No. Far kan? Different. Alright, now. But so it says that the meter length would be slightly less than 1/4 of its current length. Meaning that 0.248 should be equivalent, approximates to 0.25. So 1/4, 1/4 less. Okay. So no. All right. And nevertheless, this example is actually more or less in terms of how to use this expression, quite similar to what I have mentioned from the beginning of our Google Meet, that for physics 2, it's more on the usage of the right equation, which equation to be used, substitute into it, then you should be doing okay. Right. Okay, this is not within it. No. All right. Okay, our last two thing, damped oscillation and also resonant. All right. Number one, what is damping? Damping is more like a friction. Okay, damping is due to friction. So non-conservative forces such as friction. So it retards the motion of the system, meaning the amplitude just gets smaller and smaller. Don't need this. Hold on. Okay, let's have a look. Alright, so the purple is the restoring force direction. Let's just, okay. So this is about to, okay, look at the direction of the restoring force, always directed towards the equilibrium, and it keeps changing. Now the restoring force is in the opposite direction. Okay. So when the blocks is moving to the left, restoring force is to the right. And also with the friction, opposite direction to the movement. So object is now to the right. Okay, stop for a while. Okay, in this sense, all right, block is now moving to the left and friction is to the right. Okay, restoring force in the same direction. Okay. always directed trying to go back to the original position, and you find that the amplitude just gets smaller and smaller, and since it's slowing down, the kinetic energy also gets reduced. Right, hope it helps. Right, now basically we have three types of damping. We call it as underdamped, critical damp, and also overdamp. How to differentiate them? Now, when you say underdamped, okay, underdamped, all right, let's start with underdamped. Underdamped is the blue one, meaning that the friction is small, retarding force is small, okay, retarding force is small, okay, and therefore it will make a few oscillation before coming to equilibrium. So there was a few oscillation, 1, 2, or 3 perhaps, but a few oscillation. So this is considered as underdamped. Right, now the next one, critical damp. Okay, when it reaches critical damp, the system does not oscillate. Okay, which is critical? The rate curve. Right, this is the rate curve. It's return to the equilibrium in the shortest time possible. In the shortest time possible. Okay, that is critical. All right, exam might be asking you, sketch the three graph. Okay, the three graph for under them, the critical and also over them. Right, so you need to understand which one which. Right, while over them, the retarding force is very large as compared to the rest, and therefore, what you will find, it takes sometimes much longer time to come to the equilibrium, and it doesn't make any oscillation. All right. Okay. Last one, force oscillation. Now, force oscillation had very much to do with what we call as resonance. But number one, we need to know what is resonance. Okay, resonance. I'm done with this one. Resonance. All right. Okay, this one. Okay. Now, in this experiment, you will find that we are going to we are going to, you have to look at it. All right, let's have a look. All right, the red one is being displaced or disturbed, okay, disturbance, and the rest has started to vibrate small, okay. However, between all 1, 2, 3, 4, the one which has the same length, okay, let's have a look, with the one which has the same length, okay, everyone vibrates. Yes, this is the one, okay. The one which has the same length tend to vibrate at a bigger amplitude. All right. Now, which one is force vibration? There are two force vibration actually. The guy who displays it, he would be the one who is exerting the force initially, but afterward, the force had been transferred to the who is it? Which one started first? The red one. It has been transferred to the black one displays, okay, and then the energy was transferred to the red one and everyone. However, the red one, which has the same length, tend to vibrate at the largest amplitude as compared the rest because they have the same natural frequency. How so, madam? Remember T just now? Talak, the one that has the same L is the one. Okay, so this experiment continued. Notice that none oscillate at the larger same amplitude or almost the same amplitude because none has the same length. Okay, let's go over. Okay. right? Both has the same length, and you will notice that resonance is occurring. So in short, what is resonance? Resonance is the effect where amplitudes will be magnified, will be getting larger, because the force vibration has the same natural frequency as the object. Okay, listen, Okay, let's transfer it to yourself. Right? Your frequency is 100 contoh, 1000 hertz. Okay, let's say that you are 1000 hertz. Every object has its own natural frequency. So you are 1000 hertz. All right. Somebody is like uh, sending vibration to you, but at 500. Well, it makes you vibrate a little, but not that excited. Not that excited. However, there come another person, the second person, who now sending the vibration at 1000, because you are at the same natural frequency as the force just now. Then you will be at the resonance, and now you will be like getting excited, vibrating at the larger amplitude. So this is what resonance is all about. So the keywords just now, where there is force vibration, and this force vibration now has the same natural frequency with you, and that makes you vibrate at a larger amplitude because you now is at the same resonance as yours. Well, in daily usage, if you have a very good friends, you tend to say is that I always, my thought is always resonated with her. Whenever she said A, it turns out that I also said A, and then when we talk, we like get too excited. So that's in languages. Now let's what's next. All right. Okay. So this is what this figure 15.23 try to portray. Okay. Oh, it's omega, right? That's angular frequency. It's using the concept of angular frequency. Never mind. 2 pi f. Okay, 2 pi is just a constant. So it's still, it try to portray that every object, when the frequency omega of the driving frequency equal to the natural frequency, resonance will occur. All right. So which one is at resonance? This is something to ponder. All right. Okay, this is Tacoma Bridge. This is a bridge. Okay, this is in 1940 where a turbulence wind. So this is force vibration. The wind, okay, keep blowing. So the Tacoma Bridge is supposed to vibrate. Okay, so vibrate and oscillate. But heaven forbid, it turns out that uh, one day it's vibrating at its natural frequency, and then it led to the collapse of the bridge itself. Okay, let's to the collapse of the bridge itself. All right, your task is to watch this movie, this video of Tacoma, write a short statement, a short paragraph in my Padlets. Okay, and everyone can, like every one of you can like everyone's descriptions there. Okay guys, that's it for today's session. Thank you very much.